Hello everyone, welcome back to the session on your fourth unit. That is nothing but your process synchronization. Okay, so and deadlock. So basically, in this particular session, we will be starting the second part of your unit 4. That is nothing but principles of deadlock. Basically, this is actually a separate unit. You can consider it, and in this, we are going to discuss about the different problems the operating system may face a typical situation where the resources are held by the different processes and they are not releasing it. Means there is some kind of traffic because of which a deadlock situation arises. Okay, so basically that is what we are going to discuss in this particular scenario or this particular part 2. And remember that this is a very important topic because this is mostly faced with the operating systems. And whenever we are actually writing the programs, we should make sure that whatever the programs we are writing, those should be deadlock free. Okay, so mostly the deadlock situation arises depending upon the programmers, how they are designing or how they are programming the particular program in order to get executed in the operating system. So in the previous session, we discussed about where we have seen some different methods using which we can overcome the problem that multiple processes are not simultaneously trying to access the resources and perform their operations. Since we have a finite number of resources, we know that sorry. We know that we do have some finite number of resources, right? Our system is limited. Basically, if you talk about your system, this is limited. Limited in what sense? It depends upon different factors. Right? It is limited with respect to your memory. Whatever the memory we have, that is nothing but your RAM. Not only RAM, you can even talk about your disk, your extra disk, whatever we are using here, magnetic disk, whatever we are using for storing the information. So that is also something like 500 GB or mostly nowadays 1 TB or max 2 TB, not more than that, right? So what about the other factors? Other factors also we are having very limited, like whatever the resources we have within the system, those are also limited, right? So so that's the reason I'm saying that we have finite number of resources, and these resources have to be provided to the different processes, P1, P2, so on up to Pn. So all these processes will be using this finite number of resources, and they will be performing operation. So managing with the limited number of resources is actually a highly challenging task. And sometimes there might be a situation where we may not be able to overcome that particular problem. We may not be able to manage that particular thing perfectly, sequentially. So that kind of things is what comes under your particular deadlock state. So we will be discussing in this particular scenario, we will be, or in this particular video, we'll discuss the basic concept, exactly what do you mean by deadlock. Okay, and apart from that, we will also discuss about something called a system model. Well, in this, we will be discussing a brief introduction related to you, what exactly the deadlock situation, how it arises, how we are going to, what are the different things where this particular situation may arise, and how we are going to overcome that. That we will be discussing in the system model. So basically, and after that, we'll discuss about something called as deadlock characterization. So in this, we will be discussing about something like, what are the necessary conditions because of which this deadlock be some situation. There should be some scenario when we can say that okay, deadlock can take place in our system. So that we are going to see in this particular scenario. And later on we'll enter into, so since we are saying about deadlock means definitely we need to provide solutions to overcome deadlock. So we will be going through some different important algorithms, something related to your deadlock avoidance and deadlock prevention. We do have algorithms, and also we will be solving some problems related to those particular algorithms. Okay, so coming to the content here, basically you can see here the first thing what we are going to discuss about here is system model. Well, you can say this is a brief introduction for your deadlock. So in this we are going to discuss about introduction to deadlock. And after that we have something called deadlock characterization as I stated earlier. So here we will be discussing the necessary conditions. So whatever the necessary conditions we do have that a deadlock may arise, that we are going to discuss in this particular scenario. And after that, if you talk about, we also have something called as the most important, if you are familiar with your data structures, we have resource allocation graphs. Yeah, we are going to use a resource allocation graph. Well, these terminologies, whatever we are going to discuss here is very important because based on that only we are going to discuss the remaining portion of your deadlock. That is nothing but your deadlock prevention, deadlock avoidance, detection, and recovery. Well, basically, deadlock prevention means preventing deadlock. So we will see what exactly we are going to do happen in that particular. So we'll try to prevent it. Something we call it now, prevention is better than cure. So same way here also, we will make sure that never a deadlock situation arises. So how we are going to do that? That we are going to see in this particular scenario. And after that, we do have something called avoidance. Okay, we'll totally try to avoid that particular situation of a deadlock. So for that also, we do have some algorithms. How means we detecting whether a particular process, because of a particular process, the system is entering into deadlock state or not. If it is entering into a deadlock state, immediately we will try to avoid that particular scenario. Okay, in advance, we will try to identify whether it is going into a deadlock situation or not. If it is going, we'll simply try to avoid that particular thing. So we will see how. So here deadlock avoidance, and in case we are not able to prevent it and we are avoiding, definitely a deadlock detection will, the deadlock will definitely take place. So since the deadlock has taken place, what is the next thing? Immediately we need to detect it. We need to detect whether what is the symptom, where exactly it is located, and based on that we need to take certain action. So here these two, deadlock avoidance and detection, we do have algorithms. We have some famous algorithms here. Based on these algorithms, we will be working on different problems. Working on different problems. And remember, these problems are very, very important and very necessary to as per your exam point of view. And last one is theoretical. Okay, that is nothing but recovery. How we can recover deadlock. So here we will be provided some simple solutions, or you can call it a suggestion. Okay, these are some simple suggestions that are provided. Just follow them so that you can avoid it. Something like, nowadays, in winter season, there will be a lot of mosquitoes and there is a possibility of what we call getting malaria. So doctors generally provide suggestions what need to be done. Use, coils and all. Don't leave the water, empty or something like that. They give some suggestions. Based on that, what we are doing, we are just trying to overcome that particular scenario. So that is what he's saying. So how we can recover means here the medicines and all whatever provided that we are going to provide it. Okay. So let's see them one by one, and based on that how this particular scenario is going to work on, that we will see. Well, actually, okay, before discussing this, I just want to give an introduction. We know that our system, whatever the system we might be using, maybe your laptop or maybe your system, we know that it is purely multi-programming, right? Whatever the system of the laptop we are using, it is purely multi-programming in nature. What do you mean by multi-programming here? Nothing but that multiple processes are performing, multiple processes are performing the operation, right? So multiple processes are performing tasks simultaneously. So that is what basically we see. And we know that all these processes, whichever are going to execute it, they will definitely require resources. So well, if they are getting the resources, then only they can complete the task, right? Without getting resources, they can't complete the respective task. So here in a multi-programming environment, multiple means we have finite. So these resources are finite resources. We have limited number of resources. So whenever a particular process requests a resource, if that resource is available, we can immediately allocate to the process. But in case if the resource is already held by another process, let us suppose if this resource is held by this particular process, so we cannot directly immediately give. So we will make this process to enter into a waiting state. So I think in unit 2 we discussed about queues, right? So within the waiting queue, we are going to store that process, the waiting state. This process will enter into a waiting state. We also discussed about different states what we have, right? You people, I don't know how many of you remember. New, ready, waiting, executing, and then exit. So we already have a diagram related in the second unit. If you people are not familiar with this, I request you people to please watch my video related to your unit 2. Already I shared you the link, or you can just go to my particular YouTube channel and there you can search it. You will get this particular scenario. From there you can get it up. Okay. Now here, so any process which is requesting a resource, and that resource we cannot immediately allocate to that particular process, because that resource might be held by another process. So at that time, the requested process will be entering into a waiting state. Now what he's saying is, there are times when this particular state is never changed. Means this process is in a waiting state and lifelong this process may be has been in the waiting state itself, because of which it is not able to perform an execution, and that kind of scenario is what we basically call it as deadlock. Okay, waiting means a process which has entered into waiting state is never able to change its state further in its lifetime. That situation is what we call it as a deadlock, because he is not getting the resource what he is requesting. Maybe like, P2 has completed its execution and he has released it, but immediately P3 came. He is having a higher priority. So he is also requesting resource, and that resource is allocated to P3. Then P4, P5, so on up to Pn. All these resources are having higher priority when compared to this particular process. So he is never getting a chance to get this resource and complete it task. So that kind of situation we can call it as something like a deadlock state. Well, actually this is not purely deadlock. I will tell you what exactly the deadlock meaning is. This is one kind of scenario. Okay. So that is what he's saying in this particular thing. And moreover, it is so how we can overcome this deadlock means, one thing what he's saying is, whenever the programmer designed the program, so developers are the one who actually design the programs. Like we people are the developers, we are going to code. So when we are writing the code, we should make sure that whatever the information we are writing, whatever the programming we are doing, it is purely deadlock free. So that we have to make sure whenever we are writing the code. So here, in this case, let something give you. Now, before explaining you people the deadlock scenario, I want you people to have some brief introduction related to resources. Well, already I have explained it, but I don't know how many of you remember. So I'm just recalling it. In resources, I said that, for example, take an example of a printer. I discussed about something called as instances. Every resource will have some set of instances. Every resource will have some set of instances. For example, when we discussed about printer, I said that printer may have some 5 instances. Depending upon the printer, whatever you're using, 5 or 10 instances. What does that mean is, it will have a queue. 1, 2, 3, 4. So 1, 2, 3, 4, 5. So this is what we call it as, each block, whatever you're seeing here is what I'm calling it as instance. Okay, so every printer or every resource will have some set of instance. What does that mean? That at a time, 5 people can give an order for printing. They can directly go for printing. 5 people can give instruction for printing. Okay, so remember that not all will come at a time. The printing, the output will come, whatever the prints they have given, that will come one after another. But basically all this print means at a time 5 people will give the printing. So that will be placed in your queue. This is what we call P3, P4, P5, like this. So printer will take these responses at a time simultaneously, but when it is printing the, whenever it is printing it up, it will print one by one. So first P1, here's output will come, then process P2, P3, P4, P5. If a P6 process is coming up, let us suppose they haven't started, the printer haven't started printing. So we don't have another instance to store the request of P6. At that time, the process P6 will enter into a waiting state. So whenever the process P1 has completed, we will shift it up P2, P3, P4, P5. So what happened here now? This slot is empty now because P5 has been shifted to a further slot. So here this process, whenever is requesting, will enter here in this case. Now suppose P7 is coming. There are no slots available. P7 will enter into a waiting queue. Okay. So these queues we already discussed in the second unit. You just revise it. So P7 will enter into waiting queue here, P7. So whenever the slot is available, that P7 will come into this particular. So that is what we call it as instance. So whatever the resources we do have in our system or external resources, whatever we are using, they do have instances. Okay. So depending upon the device what we are using, that depends. Maybe 5 instances, 6, 7. So in printer, basically there are 5 instances. Means 5 people can directly at the same time, 5 people at the same time or simultaneously can give prints to that particular printer. but it will take the request and one by one it will satisfy the request. Okay, that is what basically happening in this particular scenario. Now, what is saying in this particular thing is whenever a particular process, now I mean to say that here, suppose within a room, okay, let me erase it. Suppose we have a building here. In a building, we have 9 floors. In the ninth floor, we have 2 printers. So what we can see that there are 2 instances of a printer. 2 instances of a printer, and they belong to one category. Means what we are exactly doing is we will be what exactly means to say that we know that in our system we have resources. Now these resources we are going to classify into different types. We are going to classify these particular resources into different types, and every resource, how we are classifying is based upon these particular instances. Now here we have 2 printers within a 9th floor, and we are saying that there are 2 instances of resource type printer. Now in these instances, what is saying that if anyone whoever is working in this particular 9th floor is giving print to this particular printer, they are not bothered whether it is coming from printer 1 or printer 2. Okay, because they both belong to a single category and there are 2 instances simultaneously they can give and they are going to get the print. But in case, let us suppose that among these 2 printers, one printer is in the 1st floor, okay, and another printer is in the 9th floor. Now, can the people who are working in the 9th floor can see these 2 printers as 2 instances now? Will they be able to see it? It's highly impossible, right? Because this is in the 9th floor. This printer is in the 9th floor and this printer is in the first floor. So both are located at 2 different locations. So definitely this is of another type and this is of another type. So wherever the resources are available at a same location, that we can represent as a same instance, or else we can't provide it. That is what basically he's saying in this particular scenario. So let me show you that. So that is what I have said here. You can see the thing. Okay. So if you see here, basically, this is what I have explained here. So system basically consists of finite amount of resources. So limited amount. Finite is nothing but limited amount of resources, and using these resources, what happens, these processes will be competing. So there are multiple processes we are actually creating in our system. All these will be competing for these particular resources, and these resources we are actually classifying into different types and we are representing into categories R1, R2, so on up to Rn. And every resource, okay, every resource will have some instances. As I told you, the printer will have 5 instances. That is nothing but a queue. So with 5 slots. Okay, so at a time, 5 commands from the user the system can take. I mean, for printing, it can take like 5 different people can give a printing at a time. So those 5 people you consider that as 5 processes. So P1, P2, P3, P4, P5. That is what he means to say here. So every resource will have some set of instances. Now, whenever under a normal mode of operation, whenever you are applying it, you are executing it, what is saying here is a process will perform its task based upon these 3 steps. Whenever a process is created, he has to complete a particular task. So he can complete the task using or based upon these 3 particular requests. These 3 particular steps. The very first step is request. So whenever a process wanted to use a resource, first it has to request for that particular resource. He can't directly go and what we call nab that particular resource. It has to first request that particular request from the operating system. And if that request is available, then the process will be allocated that resource and he can start using it and start executing whatever he has to do. Well, remember, in case if the resource is not available, then the particular process will enter into a waiting state. Remember that, okay? And once the process completes execution using that resource, the last step is he has to release that resource so that it can be accessed by some other process. That is what it is going to do. So any process you are creating within your system, either you are creating or the operating system itself is creating, if it wants to access a resource, it has to go through these three things: request, use, release. So whenever a process wants to perform a task, it has to request the resource. If the resource is available, that is allocated to the process, and it can start using it. In case if the resource is not available at that time, he has to wait until the resource is free. Once he's getting it, he can start using it. And once he completes using that particular resource and completed his task, then he has to simply release the resource so that it can be allocated to some other process. These are the three basic steps that are actually implemented in this particular scenario. Now, whatever I'm talking about, this request and release of resources, this is purely done using system calls. I think you people are familiar with this also. We discussed in the first unit itself, system calls, right? So what are the different system calls? We have something like, request or release. These are the methods. What do you mean the system call is nothing but methods? So request and release. These are the system calls for releasing a devices. Like if you people are calling open and close, so where we use this open and close? Obviously, we use it for opening a file and closing a file, right? Same way we have something called as wait and exit. These are the system calls we are using, and these system calls are what we call it as here release and request. I mean resources. Releasing and requesting of resources are done using basically system calls. So these are some of the system calls. Well, you people are almost familiar with this system calls. So what are the different system calls we do have? You people already know it. Just recall this when we are discussing this. Okay, I'm not going to touch each and every system call in this because we have already covered in the second unit. You people just go through it. Okay, so these all comes under in this particular scenario. Okay, let's take an example and explain you people how exactly it works. Okay, so these are the whatever I have explained you, open and close a file. So these are the methods what we have, and these are what we call it as system calls. So if you see here, request and release are the system calls. Here open and close. I forgot to close the bracket here. So open and close are the system calls. So allocate and free. These are the system calls for allocating the memory and releasing the memory. Now, so basically, what is the statement? Now, let's talk about deadlock. We were actually discussing about deadlock. That's the introduction part related to that. And now we will be discussing about what exactly you mean by deadlock. So here, we can say a set of processes. Set of processes is nothing but like, P1, P2, so on up to Pn. There are these many processes we have. So this is one set. A set of processes will be in a deadlock state when every process in the set is waiting for an event to take place that can be done only by the process within the set. Okay, this is somewhat typical. I will explain it how exactly it's going to work on. Okay, I'll take an example and tell you so that it becomes easy for you people. Let us suppose that we have 3 CD drivers. Okay, 3 CD drivers I'm having. These are the resource CD, CD, and CD. This is a resource 1, resource 2, resource 3, R. And let us suppose there are 3 processes we are having, P1, P2, P3. Please understand this carefully. Now, instantly, in the beginning, every process is having one resource. Every process is having one, and also you please focus on the arrow, whatever the arrow I'm representing, or the edge, whatever I'm representing, because we have a specific name to this particular edge also that I'll show you in the coming slides and I'll explain it. But right thing, you understand that there are 3 CD drivers we are having, okay, and 3 processes we are having. Instantly, every process is having one resource here, R1, R2, R3. Now, what happened is, after some time, this particular process requested another resource, R2, another CD. He want another CD for writing purpose. So he has requested. At the same time, this process P2 has requested this particular CD. Okay. And same time P3 have requested another CD that is have with P1. Now if you see here, this particular process is already having one, he want one more. Same way P2 is having one, he want another one. P3 is having one, he want another one. Now can you people tell me whether this particular processes will be able to complete the task? Well, I think it's highly impossible now. Why? Because this particular process P1 will not release this particular resource until he is getting this particular resource. Same way, this particular process P2 is not going to release this particular resource until he is getting this one. And P3 is not going to release this until he is getting this particular R1. So what happened here? These three processes are in right now deadlock state. They will never be able to execute the task and they will never release these particular resources. This R1, R2, R3 are now held by these three processes. Now they are not going to release the resources and these resources cannot be used by other processes. That's what the typical thing here. That is what we call it as a deadlock state. And that is what the definition related to it. See here, statement. It's set up process. We have taken three processes here. P1, P2, P3 is in a deadlock state when a set of process in a deadlock state when every process in the set is waiting for an event that can be caused by another process in the set. That's what happening here. This process P1 is waiting for an event which will be done by P2, that is releasing this particular resource. And this P2 is waiting for an event that can be done by P3, that is releasing this particular resource. And this process is waiting for an event by P1 to release this resource and they cannot release. Okay, and they are not going to release it. Then we can say that all the three processes are in a deadlock state. That's what basically is saying in this. Okay, and coming to the definition here, this is a normal definition he has given. You can just go through it. Okay, a process will request a resource. If the resource is not available at that time, the process will be entering into waiting state. Whatever I have explained in the previous slide, that is what I have represented. Now, sometimes the waiting process will never again able to change state. Yeah, I already told you. Why? Because the resource which he has requested is already being used by other processes and this fellow is not getting a chance. That kind of situation is what we call it as deadlock. Means that is a dead end or a deadlock for that particular process because it's not getting a chance to perform the operation. Much more real-time example if you want. I think you people are familiar with zebra crossing, right? You know that from four directions the vehicles will be coming up. Now let us suppose that some one of the hacker had hacked these particular red signals. I mean, whatever signals are available at a time, he has kept all the lights into green. Okay, from this direction, whatever the vehicle is coming, he has turned into green. From this direction, he has turned into green signal. Here also green, here also green, and there is a very big queue. What happens? Everyone will simultaneously start and they will come here. What happens? No one will be able to cross it now. So there will be a big deadlock. That is what we call it as deadlock. If there will be huge traffic. There will be a huge traffic here and no one will be able to perform the task and that is what we call it as a deadlock. They will not be able to cross each other. So that is what we call it as a deadlock state. I hope it's very clear. You people have understood this particular concept. So I'll show you now diagrammatically how it is going to work on. See? So what are the processes we have taken that I'm showing it? Three processes we have. So as I told you, three resources we are having. So initially I have taken example of a CD driver. Okay, CD driver. You can take any example. Let us take a printer. We have three printers. We are having three printers. This is printer one, printer. Okay, I don't want to write like this. So this is your printer one, printer two, printer three. I just represented with this. And also please focus on the diagram. Processes are represented with circle, resources are represented with rectangle. There is some specific, there is technicality in this. There is some specifications here. The reason why we are representing like this, that I will explain you in the coming slide. Okay, so please understand this. So here we do have three processes, three resources. So instantly, resource 1 is allocated to P1, resource 2 is allocated to P2, and resource 3 is allocated to P3. So the arrows you can see how it is represented. Now after some time, P1 has requested another resource, that is R2. Now P2 has requested another resource, that is R3, and now P3 is requesting another resource, R1. You can see there is a cycle formation in this particular graph, isn't it? There is a cycle formation here. I think you people can understand, yeah. Yeah, you can see here, there is a cycle formation here. So whenever a cycle comes within a system, definitely there is a deadlock. But again, I will specify it whether there is a deadlock or not. For time being, you understand that whenever a cycle forms within a graph, okay, this is a graph. This is a graph, we call it as a deadlock. A deadlock is this. Now here what happened, this particular process will not release this particular resource until he is getting this. he is not going to release this one until, I mean, this one until he is getting this one. And this P3 is not going to release this until he is getting this one. So obviously no one is going to release a resource because we have only 3 resources. And finally, definitely what will happen? A deadlock situation. No one will be able to complete the task. Finally, it enters into a deadlock that leads to a deadlock. So no one will be able to complete the task, and it will be till that particular system exists lifelong. Okay, till that time these processes will be in a deadlock state. Okay, so that's what happens here. And the next thing what we are going to discuss here is something called as deadlock characterization here. So here we will be specifying what are the different things we have. Actually, how this particular deadlock comes up. So we need to provide the characterization here. So these are the 4 conditions. Well, basically these are the 4 conditions. There are 4 conditions, and if all the 4 conditions hold simultaneously, if all the 4 conditions hold simultaneously, then the deadlock situation will come. That's for sure. Means in any scenario, if all these 4 points are there within that particular scenario, so you can simply declare that a deadlock has come up. There is a deadlock in that particular scenario. So let's see what are the points we have. First one is mutual exclusion. Well, I think you people are right now familiar with your mutual exclusion. We are actually discussing this particular thing from the beginning of your unit, right? So what do you mean by that? At a time, one process at a time can use a resource. That is nothing but if a process P1 is there, if a process P1 is allocated a resource R1, then no other process should be allowed to allow this particular resource. Means already this particular P1 is allocated to, I mean, this R1 is allocated to this particular process P1. So if another process is coming up P2 and is requesting this particular resource, he should not be given that resource. At a time, only one process can access that particular resource and perform the operation. That is what is calling it as mutual exclusion. And the next thing what we have here is hold and wait. What do you mean the hold and wait is? Let me explain the example. Okay, yeah. So there are 2 processes we have. This process is having R1, okay, and we have R2. Now this particular process is already allocated this particular resource. Now what do you mean the hold and wait is? This particular process is requesting another resource when he is holding at least one resource. That is what you mean to say hold and wait. So any process should have, okay, whichever process is requesting a new resource, he should have at least one resource in his hand. Then only we call it as that scenario hold and wait. Next, no preemption. I think you people are familiar with no preemption now. So once a process is allocated, I mean the resource is allocated to a process, it solely depends upon that process to release the resource. No one can try to preempt. No preemption means once a process is allocated the resource, no one can try to grab this resource until this process is releasing this particular resource. That is what we call it as no preemption. Then we have circular wait. Well, I already explained this concept in the previous slide itself. That is what we call circular wait. I'll explain it one more time. I have taken 3 processes, right? If you remember. And then I have taken 3 resources, R1, R2, R3. Resources are represented with rectangle and processes with this. Now here, this P1 is allocated this resource, P2, R2 is allocated, means R2 is allocated to P2, R3 is allocated to P3. Now this process P1 is requesting R2, P2 is requesting R3, and this P3 is requesting R1. This is what we call it as circular wait. Okay, I'll represent this in this way. See, P1 is requesting, okay, not like this. R1 is allocated to P1 and P1 is requesting R2. And this R2 is allocated to whom? P2. And P2 is requesting which resource? R3. And this R3 is allocated to which process? P3. And P3 is requesting which resource? R1. So this is the scenario. This is what we call it as circular wait. Okay, so there exists a set of processes. Okay, and here of waiting processes here, and such a way that P0 is waiting for a resource that is held by P1. So I have taken P1 here. So P1 is waiting for a resource. P1 is waiting for a resource R2 which is held by P2. P2 is waiting for a resource R3 which is held by P3. And P3 is waiting for a resource which is held by again P1. So this kind of scenario is what we call it as circular wait. And remember, if wherever all these four conditions are there, definitely a deadlock is there. Wherever these particular four conditions are existing or satisfying, definitely there is a deadlock in that particular scenario. That is what is saying in this particular thing. So I hope it's very clear. You people have to remember all the four conditions here. First one is mutual exclusion. Means at a time only one process can use the resource. If any other process try to access that resource, that will not be possible until that resource is free. Next, hold and wait. So any process want to request another resource, he should have at least one resource with him in his hand. Then only he can request. That is hold and wait. No preemption means a resource means whenever a resource is allocated to a process, no other process can try to grab that particular resource until and unless the process which is having that particular resource is releasing that resource. Okay, something like P1 is allocated R1, P2 is requesting R1. No, P2 cannot grab this R1. Neither the operating system can grab and give it to P2 until P1 is releasing that particular resource. That is what we call it as no preemption. And then finally circular wait. And circular wait, this is the example related to your circular wait. I hope it's very clear till here. So that's for the example. Okay, what are the previous example we have seen? That only I'm going to show you here. Yeah. So I think you people understood now. Now remember, if I just want to classify that all these steps are interrelated. If you see a circular way, don't you think this one and this one is same? Hold and wait. Now this particular process is requesting R2, but he is holding R1. And P2 is requesting R3, but he is holding R2. And P3 is holding R3 and is requesting R1. So if you see here, this condition is there. Okay, circular wait, a cycle has been formed here. Mutual exclusion means at a time one process can use. So P1 is allocated R1, so only he can use it. He is requesting, but we are not giving it. You can see all the four and whenever P1 releases R1, then only it can be allocated to P3. So no preemption is also 3. So indirectly, all these four conditions are interrelated with each other. Okay, don't think that all the four are different or separate paths they are having. All the four are interrelated with each other. Okay, circular wait and hold and wait both are mostly interrelated, and that we can see in this particular diagram. Okay, I hope it's very clear. So there is a cycle formation here, so definitely there will be a deadlock. This is the best example what we can show you in this particular scenario. And the next one what we have is resource allocation graph. Let me explain it. Then we will wind up this particular session. Now deadlocks basically can be represented well diagrammatically. If we can represent any situation, that is much more easier to understand when compared to theoretical. Same way deadlocks can be described more easily and more precisely using something called as graph. And what kind of graph we can use is directed graph. And basically the technical term given for this particular resource allocation graph is system resource allocation graph. Okay, so you people already seen the graph earlier. That is only what we are going to talk about in this particular scenario. Okay, so we can represent deadlocks using graphs. Directed graph. Remember, it's a directed graph, not using undirected graph. You cannot use undirected. We have to use directed graphs only. That's the reason in the previous scenarios you might have seen when I have allocated P1, P2, P3. Here we have R1, R2, R3. We used a directed graphs. I mean I edges. So like this, he is requesting. This, he is requesting. This, and he is requesting. You can see there is a direction here. Nowhere you can use undirected. You have to use directed graphs only. Okay, what do you mean by this particular graph now? System resource allocation graph. Okay. Now let me give a definition that actually consists of vertices, edges. We know that graphs basically consist of vertices and edges, but we will be classifying these vertices into two types. One is P, another is R. Few people are already familiar, I think, by the time. So I think you understood now. What do you mean by P here? What do you mean by R? So P is nothing but the set of processes. P1, P2, P3, so on up to Pn. What about R? You people understood now. Resources. R1, R2, so on up to Rn. Yes. Now, since we are representing vertices into two forms, definitely there should be some changes, right? There should be some difference between a process and resource. That's the reason we are representing a process using a circle, and we are representing the resource using rectangle. That's the reason I'm drawing. You can see the process, whatever I'm showing you here, P1, P2, P3, I have represented using circle. But what about the resources I'm using here? I'm using a rectangle to represent it. So that's the reason. So to classify this vertices. What about edges? Edges, okay, we will be having two different types. Okay, I will clear it and I'll show you up. So that's what I'm going to represent here. Vertices are classified in two types: process. Okay, P and R. P is nothing but set of processes. R is nothing but set of resources. Now coming to the edges, edges are also classified into request edge and assignment edge. What do you mean by that? I'll explain it. So we previously explained P1, P2, P3, R1, R2, R3. Now, P1 is requesting, okay, P1, now you can see here there is a difference in the way arrows have been represented. Now R1 is already allocated to P1, right? That is what we call it as assignment edge. Assignment edge. Now P1 is requesting this particular resource. That is what we call it. So this resource, this arrow is what we call it as request edge. Technically, how can we say it? If an arrow goes from Pi to Rj, means if a process Pi is requesting a resource Rj, so arrow goes like this. This is what we call it as request edge. Request edge. Now, if a arrow goes from Ri, Rj, like this in a reverse direction, we call this as assignment. Means this particular resource is allocated to this particular process Pi. This particular resource is allocated to this particular process Pi. That's what he's saying here. You can see here Pi, the arrow is going towards resource. From process, the arrow is going towards resource. We call it as a request edge. And from the resource, if the arrow is going towards the process, means that is an assignment edge. So whenever a process requests a particular resource, then it will be represented like something, P to R. And once the operating system assigns this resource to this particular P, then the edge will be converted into this particular direction. That's what it's saying. Okay. But basically here, we are saying that resources, whatever I'm representing, they have instances. For example, I have taken example of a printer. Printer has 5 instances. Now, this is a printer 1, printer 2, printer 3. So, how many instances we do have here? Every printer has 5 instances. So, we have 3 printers. So, 3 into 5, 15 instances we have. So, how we can represent these instances is nothing but within this particular resource, I am going to represent with the 3 dots. I am going to represent 3 dots. And these dots are what we call it as instances. Okay, I hope it's clear. Every resource will have 3 instances like this we are representing. So all these 3 dots, whatever you people are seeing here, is what we call it as instances. That I will show you in the coming video. Coming slide. Yeah, you can see here, I am using here 3 different resources here. So this is one resource, another resource, another resource. Now here, this resource is having only a single instance. This resource is having a single instance. But if you look at this particular resource, he is having 2 instances. Means at a time, 2 processes can use this particular resource. But whereas coming to this particular resource and this one, only one process can at a time use it, because they are having only a single instance of that particular resource. Okay, let me erase it up and then show you. You can see here, this is the diagram. So using this diagram, I'm going to classify into what are the different processes we have, and then whatever the pairs we are having, that I'm going to classify it here. See here, Okay. So there are three processes we are having here. You can see here P1, P2, P3. We have R1, R2, R3 and R4. There are four resources we are having. Now every resource is having some set of instances. R4 is having three instances. Means at a time four processes can use this resource to complete the task. Whereas coming to R2, two instances. Means at a time two processes can access this particular resource and perform the task. Whereas coming to R1 and R3, we have only a single instance. Okay, now P1 is given one instance of R2. Okay, so here, okay, I have represented the sets here. So P, R, and E. I think you people are familiar now. P is nothing but process, R is nothing but resource, and E is nothing but edges. So what are the processes we have? P1, P2, P3. What about the resources R1, R2, R3? Now edges. What are the edges we have? So P1 to R1. P1 is requesting. So P1 here is requesting resource R1. So I'm representing like this. P2 is means P2 is requesting R3. You can see here. P2 is requesting R3. So next R1 is allocated to P2. You can see here R1. R1 is allocated to P2, right? So that is what represented in this way. So you people can simply write it up, whatever is there. But one thing I want to say here, you please understand, whenever a particular process requests a particular resource, that arrow should reach only to the border of that particular rectangle box of that particular process. But whenever that particular resource is allocated to a process or the instance of a resource is allocated to that particular process, then it should come directly from that particular dot inside. You can see this resource instance is allocated to P2. So it is coming from inside. Now this process is requesting this particular resource, so it is only going till here. This you people have to be familiar with. If you make mistakes here, there is a chance that you may be losing the marks. So please understand this. Okay. Yeah. And after that, we have something called as resource instance. Okay, who is actually handling which resource that we are representing here? We can see that how many instances we have. So R1 is having how many resources? One. R3, one. R2 is having two instances. And R4 is having three. That is what I have represented here. You can just go through it. And finally, the state means which process is holding which resource and which process is requesting which resource. So if you see here, we have three processes. So if you talk about here, process P1 is holding an instance of R2. So you can see here, one of the instances allocated to, so that is he is holding and is waiting for an instance of resource of R1. So he is requesting this instance, that is what is saying. What about P2? You can see here, P2 is holding an instance of R2 and is requesting R3. That is what represented here. What about P3 now? P3 is actually requesting, I mean, he is holding only R3. So that is what is represented in this particular scenario. So this is the way how you people can define. So what are the symbols we have based upon the diagram? We have classified into different sets. What are the instances we have in a resource? What are the different sets we have? And what are the different process states we are having? You people have to write this in your exams. Okay, so just go through it perfectly. Same diagram I am going to take here. Okay, in the previous diagram, I just want to say, I said that there is a cycle. If there is a cycle here, formation, then definitely there will be a deadlock. Now here, when we are talking about server instance, if remember, if there are only a single instance of a resources, like for example, R1 is having single, R2, R3 is having single, R2 is having a single instance, and R4 is also having single instance. And then if there is a cycle formation takes place between them, then definitely there is a deadlock. Now I'm going to change the scenario. In the previous slide, I told you that whenever a cycle forms, then a deadlock situation, I mean, there is a deadlock. But now what I am saying here is, whenever there is a single instance of a particular resource, means R2 is having two instances. Assume that there is only one. This is not there, this is not there. Only one instance is there. Same way R4 is also having only one instance like this, like the way R3 and R1 is having. Then if there is a cycle in this, then definitely there is a deadlock. But if there are multiple instances, multiple in the sense like the way the diagram is representing, then if there is a cycle, that then we can say that there may be a deadlock, but not sure. When there are multiple instances of resources are available like this 3, 2, okay, then if there is a cycle formed in this particular diagram, then we cannot say that there is a deadlock. there may be a deadlock. Not sure about it. There may be a deadlock, but it's not that a deadlock is there. That is what he's saying in this. Okay, I'll explain this with diagram so that it becomes easy for you to understand. Like in the previous example, in the previous example, what we have seen, we had three processes, right? P1, P2, P3, and we had resources. So R1, R2, R3. So P1 is having, so there is a single instance that is allocated to it. He is requesting this one. This is there with P2, and P2 is requesting P3. P3 is there with this particular, R3, and this is there with P3, and P3 is requesting R1, and that R1 is there with P1. So what happens here? There is only a single dot. Single dot is present there. Means only one instance is there. That's the reason it's not able to. Means that scenario is what we are calling it as deadlock. But in case if I represent like P1, P2, R1, R2, P3. Okay, I'm taking the same scenario. Okay, where is R3? Okay, let's take this as R3. Now, in case if you assume that there are two instances here, like this, every resource is having two instances. Now, P1 is actually allocated one instance, like this. Now P2 is allocated one instance. This is R2. And from R3 is allocated one instance to this particular processes. Now, in case if the P2 is requesting R2, there is already one instance available freely. Immediately that will be allocated to it. So you can see there is a no deadlock situation. You can understand this. Suppose P3, he is having one instance, he is requesting R1. Already one instance is free. Immediately that will be allocated to P3. What will happen now? There will not be a chance of a cycle formation here. That's what he means to say. If there are multiple instances are present within a resource, then if a cycle forms, then that doesn't lead to a deadlock. There may be a deadlock, but it's not necessary that the deadlock will definitely take place. That's what is saying in this particular scenario. And that's what has been explained in this particular diagram. You can see it, graph with a cycle, but no deadlock. Why? See here. Now we have two resources, R1, R2. Okay, there are two instances here. Here also we are having two instances. Now P1 is requested, okay, P1 is having one instance of R2 and he is requesting R1. But R1, one instance is with P2, one instance with P3. Now if you talk about P3 now, P3 is requesting one instance of R2 which is with P4. So there is a cycle here, P1 to R1, R1 to P3, P3 this, isn't it? There is a cycle here. You can see here, okay, let me write it up so that it becomes easy for you people to understand how the cycle is going. See, P1 is requesting R1 and that R1 is with P3 and I'm talking about a cycle now, P3, and P3 is requesting R2 and that R2 is with P1. So there is a cycle here, you can see here, isn't it? Now cycle forms. So can you see there is a deadlock now? Is there a deadlock here? Well, you can't say there is a deadlock. Maybe there is a possibility that deadlock may come, but it's not a deadlock necessary that a deadlock is there. Why? Because see, if you consider this particular process, he is having one instance of a resource R2. Now he is not requesting any other process now, resource. Now in case whenever this particular process completes its task, he will release this particular resource. Now this particular resource is free, right? Isn't it? Now, can the operating system allocate this resource to this particular process? It's possible. Yes, it is going to give it. Now, once this resource is given to this, process P3 will release this particular resource, isn't it? And now this can be allocated to this P1. Same way P2. P2 is holding this particular resource, but he is not having or requesting any other resource. So once he completes, this is also free. So that also can be allocated to P1. So even though there is a deadlock cycle, there is a cycle formation here, but that doesn't necessarily make a deadlock situation. Okay, so that is what he's saying. If multiple instances are there, multiple instances are there in a resource, then there may be a deadlock. May be a deadlock, but it's not sure. Okay, but if we have single instance of a resource, if we have a single instance of a resource and a cycle is forming, then definitely it is a deadlock. Like instead of two, we have only single dot. Instead of two, we had a single dot. There is a cycle formation. Definitely there will be a deadlock. But since we have multiple instances, two instances in one resource, so there is no possibility. There is, or means there may be a possibility of deadlock, but that's not sure that deadlock will definitely arise in that particular scenario. That's what he's saying in this particular thing. Well, this is what I'm saying here. See, basic fact, what we have, if a graph contains no cycle, there is no cycle at all, you can say that there is no deadlock. But in case if a graph contains a cycle, the way we got here, then if only one instance for resource type is there, then deadlock takes place. Like here we have two instances, multiple instances are there. Instead of multiple, we have only a single instance. Forget about the blue dot. If only there is this instance, this is consider the red dot now. One instance is there, then definitely there is a deadlock. But if several instances for resource types are there, means this blue dot, two instances are there for R1, two instances are there for R2, then there is a possibility of deadlock, but there will not be surely a deadlock. Okay, that is what is beautifully explained in this particular scenario. Please remember this. These are very important points. Okay, if there is a, cycle in the graph, if there is a single instance of every resource we are having, then definitely deadlock will take place. If there are multiple instances are present in a resource type, then there is a possibility of deadlock, but not necessary that a deadlock will take place. Only when there is a condition, there is a cycle formation. Okay, so there are different methods we have. Well, we will discuss this in the coming session. Okay, I don't want to discuss here and this. Only 1-2 slides are there. So that we will discuss in the coming session. So in this session, we discussed about briefly introduction about what do you mean by deadlock and what are the terminologies we are going to use in it, how the resource allocation graph. So please go through this particular video thoroughly because whatever I have explained in this, we are going to use it in our coming video sessions. And in that, I will not be explaining again and again. So you please understand, like, how to represent the process, how to represent a resource. Whenever I'm representing an arrow from a process P to resource R, what does that mean? Assignment edge. If a edge is coming from resource to process, that is a assignment edge. If a edge is coming from process to what we call resource, then that we call it as a request edge. So that you should understand it. Please go through this particular video. And if you like this video, please do like it and share it up. Thank you. Thank you for watching.